This is section 12.1, inverse variation. Okay, so inverse variation is a type of variation written in the form y equals a over x, or y equals a divided by x, where x is not equal to 0. So if you remember, we talked about direct variation, which is written in the form y equals ax. Okay, so direct variation and inverse variation both have a constant of variation, and that's a. Okay, the biggest difference is that direct variation, you'll notice I have these pictures here. If the x is increasing, the y is increasing. If the x is decreasing, the y is decreasing. So it's directly related, right? The more hours you work, the more money you make. Inverse variation is the opposite. So if x is increasing, then y is decreasing. Or if x is decreasing, then y is increasing. So it's always going to be the opposite, right? So one good example is if you're driving and you're going faster, the faster your speed, the more gas you're using. So the faster your speed, the less gas you have in the tank. That would be inverse variation. Okay, so to give you some more examples, direct variation, so for example, your caloric intake versus weight. The more you're taking in, the greater your weight. The more exercise you do, the greater your weight loss. So the amount you exercise is increasing and the amount of weight you've lost is increasing. Also, study time and grades. So the more time you spend studying, the higher your GPA. Remember, direct variation graphically has to go through the origin. Okay, and it could look like either of the two at the bottom. And inverse variation is going to look a little different. But for some more examples, we have driving speed and time. So the faster you go, the less time it takes you to get somewhere. So your speed is increasing, your time spent driving is decreasing. And then driving speed in gallons of gas in tank, which I talked about. Another example we have here is Pacific Ocean temperatures. So as you get deeper into the ocean, the depth is increasing, your temperature is decreasing. So when you have inverse variation, that creates kind of a different looking graph, which is called a hyperbola, and it's going to look like either of the two at the bottom. Notice that it's never actually going to touch the x and y axis, it's just getting really, really close. So those are asymptotes that it's approaching, but inverse variation has to look like that when you graph it. We have another example up here in the middle where we have a direct variation and inverse variation on the same graph. So notice the red, as x is increasing, y is increasing. For the blue one, as x is increasing, y is decreasing rapidly. Okay, example 1, tell whether the equation represents direct variation, inverse variation, or neither. A is neither because it is in slope-intercept form, and remember this means that it's crossing the y-axis at 1, which means that it's not going through the origin. So that can't be direct variation and it's not inverse variation. For B, that's going to be direct variation because it's of the form y equals a number times x, so y equals negative 3x would be direct variation. C, this is a very common way to see inverse variation, but just to show you why, remember that inverse variation is of the form y equals a divided by x. So if I get y by itself, I divide by x on both sides, I get y equals 2 over x. So that's going to be inverse variation. Okay, just like with direct variation, if we know that we're trying to find an inverse variation equation, given x and y, we can find the constant of variation. So remember, it has to be of the form y equals a over x. Alright, and we know x is 4, and we know y is -6, so I'm just going to plug it in, and then solve for a. And to solve for a, I want to get a by itself, so I multiply by 4 on both sides, and a equals -24. So now my inverse variation equation is y equals -24 divided by x. And then part B is asking me to find the value of y when x is 2. So y equals -24 over 2. So when x is 2, y is -12. Okay, and for our last example, the owner of an electronics shop determines that the demand for computers, represented by D, varies inversely with the average price of computers, represented by P, where the average price is $750 and the demand is 250 computers. So find the inverse variation equation, and then we're going to use that to find something else. So first, for the inverse variation equation, remember it has to be of the form y equals a over x. In this case, instead of y and x, we have, okay, so we have D varies inversely with P, so we have D equals A over P, and we can plug in a price of $750 and a demand of 250, so 250 equals A over 750. Solve for A, we're going to multiply, and we get 187,500. So our direct variation equation is my inverse variation equation over, well, actually, make that D over P. So then what is the monthly demand when the average price is 500? So we're just going to plug in D equals 187,500 divided by 500, and you get a demand of 350. Sorry, 375. So the demand when the average price is 500 would be 375 computers. In this case, it says D varies inversely with P, so I wrote it D equals AP. Had I written it the other way around, I would have actually gotten the same constant of variation, because you're going to multiply to get A, and it's the way that the graph is set up that makes it so that it really doesn't matter which way you read it. You would still have gotten the correct answer. And that's it for this section.